Everybody, I think it's just about 4 o'clock. My time is right here. Hello, good afternoon. And I hope you're having a good day so far. Is it hot outside?
A little bit.
I played basketball yesterday. I was absolutely drenched in sweat after that. Crazy, but maybe today's a little bit better. Would have been a better choice, except that, that nice calm first couple of weeks of every semester. That's long gone now. Things are in crazy mode for me at least. I just had to give an exam for my other class today, and over there behind my little computer is a mountain of papers that is waiting for me. I am going to be very busy with that, as I literally have about 80 students between the two classes, so that's a lot of work for me. So to help me out with that, so I don't have my entire weekend ruined by the grading, I am going to cancel my office hours tonight. I don't like to do this very often, but I would like to get off of campus ASAP after class and just start getting this done. However, I am aware that you guys are working on a homework assignment. Obviously, I'm not going to be grading it tonight because I'm going to be grading that tonight, probably through most of tomorrow as well. So what I've decided to do, there's no reason to have you turn in the homework if I'm not even going to be able to look at it. I do know that at least 2 people have turned in something into Canvas already. If that was you and you realize that you'd like to have a little more time to work on it, feel free to do that. I'm going to give you until tomorrow night to finish this. So due on Friday at the end of the night or whatever. And what I'm going to do, since I can't have office hours tonight, I'm going to do 2 things. One is I'm going to take some questions from the assignment during class today, or at least give you some hints to maybe talk about a little bit of it. The other thing I'm going to do is I'm going to add some office hours for tomorrow, but I'm going to do it a little bit later because I'm going to be still working on those for the first half of the day. So I'm going to have some Friday office hours. In fact, I think on my syllabus it says I usually have Friday office hours. I might start around 7 o'clock tomorrow, and I'm gonna try to go till about 10 in the evening. So feel free to drop in if you're still kind of struggling through any of it. There are a couple of problems I think that are a little trickier than maybe average for the homework that you've done up till this point. So if that's the case, we can talk about some of it here today and also on my office hours tomorrow night. Does that sound like a fair deal? Yeah. You're all okay if I skip town tonight? Not skip town, skip office hours tonight. Okay, that might be good for me. I'll feel better if I can get that load off of my shoulders sooner. And I do much better when I am not grading just in my office. I like to get off campus and change up my scenery. It puts me in a better mood, as good of a mood as I can possibly be in with this kind of work in front of me. Anyway, it's always the worst one, first midterm, because everybody's there. It's the maximum size of the papers I'll ever have to deal with. Anyway, okay, so that's all I've got. Now, next week, there is another homework assignment due, and that will be due on Thursday. I'd like to try to stick with Thursday for that. And I don't think next week's assignment is going to be as much of a, I don't think there are as many sort of kind of weird oddball questions there. So I hope next week's assignment will go a little bit easier. But anyway, we'll have time to work on that, obviously, going forward. So I'm going to just leave it at that for now. Don't forget, I put up that midterm review packet the next 4 days over the weekend. If you haven't had a chance to kind of just at least browse through that a little bit, I'd recommend it. At least get my office hours written down and the review sessions, and kind of get yourself organized as to what you're going to do to get ready for that exam. But anyway, that's still not till the Tuesday of the week after next week. So we've got some time on that. Okay, so these are all the important announcements. And if I don't erase them too quickly, even Sergio will.
You said 7 p.m. is a maybe. It's not.
Oh, it should be 7. I think it should be there. I'm just kind of thinking about when I would be likely to be back. Yeah, I think 7 o'clock was good. I mean, if you go in there and I'm not in there right at 7, just try me 5 minutes later. Yeah, I think it should be pretty close. Okay, any other questions before we get started on the actual math today?
How are you feeling?
How am I doing? I'm doing okay right now, but I'm looking at this stack of papers and kind of not looking forward to that. It's the only part of this job I don't really like that much. I love everything else. But once a month I have to, put up with this and, it just
You're good, I get double that.
comes with the territory. Yeah, I'm sure you probably do. Yeah, some of you probably don't have too much sympathy for me. Anyway.
I wish I had 80.
Yeah, right, it'd be nice. Anyway, let's see, on Tuesday, we started chapter 6. I'm gonna spend the first part of class kind of just doing some more of this inclusion exclusion principle. And then we will save some time to look at the homework that's due. Now it's due tomorrow night instead of tonight. We'll look at some of that a little bit later in the period. So I wrote it up again, same thing we had on the board on Tuesday. If I have M sets, these are A1 through AM, and I would like to know the size of the union. The union is usually indicative of sort of a condition that's based around the word or. So one option or another option or another option. You'll see that usually in the wording of those questions. Then in order to figure out how many elements are in that union, we do this sort of alternating sums of smaller sets. So first of all of the singletons, we just add up the sizes of the individual sets. We soon realize that we've overcounted a lot of things. We have to subtract out some of the things that have been counted more than once. And we do the pairwise intersections. These are distinct sets, so notice that I is less than j, right? So I'm choosing two different subscripts and finding the size of the sort of the two-way intersection of those sets. But then we will have subtracted too much back out, so we have to add some things back in again. This is the three-way intersections. AI intersect AJ intersect AK. Again, IJ and K are distinct, ranging from 1 to M. And we just keep going like that till we sort of get to the end. The end is where you have all of the sets intersected, right? And that last term might be a positive or a negative. It actually depends on how many sets you have. So we have to keep track of that as well. But it's a plus or minus of the size of the intersection. This exponent here is, I've got it correct here, it's M plus 1, M plus 1, okay? So if M is even, you'll end up subtracting the last term. If M is odd, you'll end up adding the last term. That's basically how it's going to work out, okay? So that is that. Let's try, we did one example of it on Tuesday, but I'd like to warm up with just another practice example, and I've got it written down here. The question is, how many positive integers that are less than or equal to 10,000 are divisible by 4, 5, 6, or 8? Okay, so you can see that word or in there, which I always talk about, and that suggests that we're going to be taking a union. And I'd like to set that up here. So I guess I'll start my solution here so that I can keep my announcements on the board for a little bit of time anyway. And so what I would recommend on something like this is that you set up your sets. Like I would actually try to take this word problem and create sets that sort of go with it. So for instance, I would probably do the following. Well, maybe one of you wants to suggest what would maybe be a good choice for a set that we could make. Jose?
Of the integer divisible by 4.
Okay, the set of positive integers x such that, and I'm going to add that it's x less than or equal to 10,000, and these are positive integers. Less than 10,000 and divisible by 4. I'll write it this way: 4 divides x. Okay, so we have that as a set, and then once you kind of realize that that's a natural way to get started, the remaining sets are also pretty easy to imagine because we have 3 other divisors here, which are 5, 6, and 8, and so I can go ahead and try to use those as well. Sorry, I'm just going to make sure I've got my volume up on this thing. Yeah, okay, we're good. Okay, so the set B would be, I'm just going to do a ditto symbol and put 5 divides x. And then C is the set of positive integers less than or equal to 10,000 such that 6 divides x. And D is another set, this time those integers for which 8 divides x. So we just make the 4 sets like that, because now we can rephrase the problem as really being asked, what we're really being asked here, guys, is what is the size of the union of these four sets, right? So the numbers that are less than or equal to 10,000, positive integers less than or equal to 10,000 that are divisible by at least one of these, okay? So this one, this one, this one, or this one, okay? So far, so good? All right, okay, so let's try to, oh, I'm already into the solution, sorry. So then let's just go ahead and write down, the size of this union of A, B, C, and D. Okay, so we're going to first add up all of the singletons. So can somebody tell me in the numbers from 1 to 10,000, how many of them would be divisible by 4?
Two
If you
thousand
don't
five
know the
hundred.
answer, then I'm gonna make you take my number theory class next semester.
2,000.
I'm teaching math 430, so we'll, pardon?
2,500.
2,500, okay, so that is exactly right. 1/4 of them, right? Every fourth number would be divisible by 4. So 4 would divide that. All right, let's keep going. And I'm writing these down in order. So the size of A, the next one will be the size of B. How many are divisible by 5?
2,000.
2,000, right? So we take 10,000, we divide by 5, we get 2,000. All right, how many of them are divisible by 6?
1,600.
You know, if I take 10,000 and I divide by 6, Jose, I think I get 1666.66 going forever, right? So should it be 1666 or should it be 1667?
I think it's the floor.
You think it's the floor function, and you're absolutely right. I mean, you look at these like, oh, I want to round that up. But actually, it's only every sixth number that is divisible by 6, and it doesn't start until you get to the last one of those 6. So the 1,667th number would actually be more than 10,000. So we don't want that. So we're just gonna get 1,666. That's exactly right. Okay, great. And what about how many numbers are divisible by 8? Yeah, 1,250, that goes evenly into 10,000, so that's an easy one. Now let's start subtracting the pairwise intersections, okay? So this is purely a number theory question, right? So I want to look at the intersection of A and B. By the way, do these in order, so alphabetical order if you would. So starting with A, I'm going to intersect it with each of the other 3. So A intersected with B, these are numbers divisible by both 4 and 5. How many would there be?
500.
If I'm divisible by 4 and by 5, then I'm actually divisible by 20, right?
5.
And so 20 goes into 10,500 times, right? So this should be 500. The numbers are getting a little smaller as we go. Okay. Let's talk about the intersection of A with C. These would be numbers divisible by both 4 and 6. That means that they should be divisible by what other number? Or 12, or 12. So we actually just take the LCM of the 2 numbers, not the product. So you'd have to take 4 and 6, the least common multiple of those is 12. So the first number that's divisible by both of them is 12, right? Okay, so every 12th number is going to be divisible by both 4 and 6 in this list of 10,000 numbers. So what do we get when we take 10,000 and divide it by 12?
833.
833, there's probably a decimal on the end of that, but again, we don't need the decimal part, or we cannot use the decimal part because the extra kind of spills over past 10,000. Okay, what about the intersection of A with D? These are numbers divisible by both 4 and 8. Sorry? It's just the same as the numbers that are divisible by 8. If I'm divisible by both 4 and 8, well, then I'm just divisible by 8. And so that would be 1,250. So we're literally subtracting out everything that we added a moment ago. Okay, let's go on. What about B and C? So numbers that are divisible by both 5 and 6 would have to be divisible by the least common multiple of 5 and 6, which is 30. Okay, so every 30th number is going to be divisible by both 5 and 6. And if I take 10,000 and divide it by 30, I think I'm gonna get something like 333.
Yeah.
With a little decimal on the end of it, which we again ignore. So minus 333, okay? And then the next one would be 5 and 8. So numbers divisible by both 5 and 8, those don't have any common factors. So this would be numbers that have factors of 40 in them. If you're divisible by 5 and divisible by 8, you have to be divisible by 40. Okay, so out of 10,000 numbers, every 40th number would give you 250 of those. Okay, and then finally C and D. So we're looking for numbers that are divisible by both 6 and 8, which means they have to be divisible by what number? 24, the least common multiple of 6 and 8, which is 24. If I take 10,000 and divide it by 24, does anybody have a number for me?
416.
Yeah, that's what I have, 416, okay, 416, so we subtract that. Okay, stop me if I'm going too fast, is everybody following this? It's almost, most of this is just a number theory question, right? Now we have to start adding the three-way intersections. So A, B, and C together. So if a number is divisible by 4 and 5 and 6, then what single number is it divisible by? Well, if it was just 4 and 6, we would have said 12, right? So this number has to be divisible by 12 and also divisible by 5. So there's a factor of 5 and a factor of 12. Those two numbers have nothing in common, so we can multiply 5 times 12 and get 60. Every 60th number will be divisible by all three of 4, 5, and 6, right? So if you take 10,000 and divide it by 60, you get 166, I believe, with some change on the end of it, which we ignore. Okay, super.
Wait, are we missing a pair that we didn't subtract?
Oh, I should have 6 terms subtracted, that is for sure. I subtracted
Oh,
this one.
You have the 416 down there. 1, 2, 3, 4.
Oh,
5,
yeah,
6.
it's just down here.
There's 6.
I
Oh.
just put it on the bottom line and just didn't have quite enough room to write 6 numbers there.
Oh, because I was looking pairwise. We have A and B, A and C, A and D, B and D, B and C, but not C and
B
D.
and D is this one.
Oh,
It's this one here, 416.
wouldn't that be 7 terms?
No, there's only 6 of them.
Okay.
There's 4 choose 2 ways to
Oh.
choose 2 of the 4
Yeah.
sets to intersect, and that is 6. So there would be 6 terms here that all have minuses in front of them, and I've got them listed here.
Oh, okay.
I don't think I'm missing anything. Now I'm doing the three-way intersections. We got A, B, and C. Now what about A, B, and D? So numbers divisible by 4 and 5 and 8. Well, the 4 we can kind of just not worry about it, because if a number is divisible by 8, it will already be divisible by 4. So it's really whatever we got for the intersection of B with D, which would have been 250, right?
Yeah, I think so.
Yeah, so that's 250 added back here as well. Okay, so that's the intersection of A, B, and D. And then the next one would be the intersection of A, C, and D. And again, we can ignore the A and focus on C and D. Numbers divisible by both 6 and 8. Well, that's basically C intersect D, which was the 416 that we subtracted here, right? So these sets, some of these sets are
Oh.
identical.
I see.
So that whatever the numbers were are just getting repeated twice. Finally, B, C, and D. So numbers divisible by 5, 6, and 8. This is an interesting one. The 6 and the 8, we did that before. Those numbers were the ones divisible by 24. And 24 has no common factors with 5. So that means that we're looking at numbers divisible by their product, which is 120. Right, so every 120th number will be divisible by all 3 of these. What do we get if we take 10,000 and divide by 120? 83 with some change, obviously. And so that's plus 83. Now, having struggled so hard to figure that out, as soon as I go to the 4-way intersection, I'm intersecting all 4 of them. But again, I don't need to think about the first one really, because it's absorbed by the last one. So you're just going to get the same number again on the 4-way intersection, because it's really B intersects C intersect D again. So there it is, and I did work this out. If I've done it correctly, I got 4,666. That looks like what anybody else has. Andrew's got a calculator, so I know we're gonna, I know we're gonna get it right. Yeah, so hopefully that'll work out good. We'll let him confirm that for us, and in the meantime, I'm gonna, great. Does everybody understand most of that? Is there any question about it? Seems okay. So if a number is divisible by a list of other numbers, then it has to be divisible by the least common multiple of that list of other numbers, and that's sort of an if and only if condition. It's a little number theory thing. Okay, if we're good on that, I have one more I wanted to do that is this one. Yes, let's try one more example of the inclusion exclusion principle, and then we're going to actually prove it, because actually I have not proven that yet. Not the general. I have not proven the general version of it. I might have proven with a Venn diagram, a little baby version of it on Tuesday, but we haven't proven the general thing. So we'll do that after we do this example. So here's the next example. How many ways are there to distribute 25 identical stuffed animals to a 3-year-old, a 4-year-old, a 5-year-old, and a 6-year-old. Okay. How many ways can you distribute a stuffed animal to a 3-year-old, a 4-year-old, a 5-year-old, and a 6-year-old if each child cannot have more animals than their age? Give everybody a chance to jot that down. It's a little word problem here, but we're gonna pretty quickly turn it into a less wordy problem. So the 3-year-old can't have more than 3 stuffed animals. The 4-year-old can have at most 4 stuffed animals. The 5-year-old can have at most 5, and the 6-year-old could have at most 6. Okay. So let's check this out. For the solution, I'm going to rephrase this as a little equation to solve. Okay, so we could let x sub I denote the number of stuffed animals for child I. So the ith child could have that many stuffed animals. And so then what we are given, if we use that notation, we are given that in total, these things have to add up to in total, these things have to add up to 25 stuffed animals. Something is bothering me about this problem.
7, make it 25.
Yeah, I'm not missing a 7-year-old, but I do have a problem that isn't making sense to me. Because if I can only give the first child 3, at most 3, and this one can only have at most 4, and this can have at most 5, and this can have at most 6, how many animals is that? 3, 4, 5, and 6 adds up to 18. So there's no way that this could actually add up to 25, which must be why in my notes I changed it from 25 to a 16. Can we come back? Sorry, instead of 25, I mean, so the answer to this question, the way I have it phrased now, would have been 0. Okay, so let's make the problem more interesting and make this 16 stuffed animals, not 25. Is that a little better? Now it at least has a chance of making sense. So we're given that this is the equation we want to solve with, so x1 should be at most 3, x2 should be at most 4, x3 should be at most 5, and the fourth child would have at most 6. So the child 1 is the 3-year-old, the second child is the 4-year-old, and so on and so on and so on. So something kind of like that. Okay. How do you suppose I'm gonna try to approach this problem? Sam? Stars and bars, okay, exactly, because you know, you're gonna make 3 bins. And you're gonna put stars in the different bins, so maybe the first child gets 2 of the stuffed animals, the next child maybe also gets 2, and so on and so forth. You're gonna have to use up most of your stars pretty quickly to get this to work. The fourth one would have at most 6. And I only have 14 stars there, so I better give somebody else some more stars. I can give this one 2 more. There's actually not gonna be very many choices even with 16, because you've got to get this to add up to a pretty big number given these constraints. But at any rate, let's just see how this works out. Okay, so stars and bars, definitely. So we're gonna use stars and bars. And any other thoughts about the strategy, just sort of on a big picture idea before we jump into all the calculations?
Change of pairs.
We can change variables. I usually use change of variables when the condition is that xi has to be at least a certain number, because then what you do is you subtract those minimums from the total 16. So I probably don't need to do that here. Jose? Violations, yes, that's what I was looking for. We're going to actually subtract the violations, and there are 4 types of violations, any one of which has to be subtracted. So I'm gonna create a set which has solutions where x1 is bigger than 3. I'm gonna take another set where x2 is bigger than 4, and so on. Those are 4 sets. Any one of those being violated is something that we must remove, and so we would basically be subtracting the union of those sets. That's how we're gonna set it up. So we are gonna do inclusion, exclusion, but on the violations part, okay? Rather than the thing we're actually counting. So let's come back over here so I can actually write some of that. Okay, everybody follow that? Does that make sense? Okay, so this is, oh, I kind of want to keep my theorem there because we're going to prove it soon. Okay, so let's make some sets to represent these 4 situations here. So I'm going to let capital A be the set of solutions with x1 greater than 3. Okay, and then I'll let B be the set of solutions with x2 greater than 4. And then I'll let C be the set of all of the solutions that have x3 bigger than 5. And then D would be the set of the solutions with x4 greater than 6. Right. And any one of those is a violation. So the number of violations, right? The number of violations is the size of that union. By the way, before we subtract the violations, maybe we should just figure out what the total is that we're subtracting the violations from. So the total without constraints, if we didn't have any constraints on our variables, and we just wanted to know how many ways are there to solve this equation using non-negative integers where they have to add up to 16, what would the answer be?
19, choose 3.
19, choose 3. There's going to be 3 bars, and there's going to be 16 stars, right? And we're not doing any constraints, so that means we just have any possible configurations of stars and bars. So this is just 16 plus 3, choose 3, or in other words, 19, choose 3. That's with no constraints at all. Okay, sweet. Now we're gonna subtract this big giant union again, which is gonna give us a bunch of terms. All right, so next, let's look at the size of A union B union C union D. These are the violations. And again, I'm just gonna start listing them out in alphabetical order, starting with singletons and then pairwise and so on. So the size of A, these would be distributions that are required to have the first child getting more than 3. By the way, more than 3 just means at least 4. So you're going to give that child those 4 stuffed animals and then start over, right? You basically have no choices. It's like going into the grocery store to get the 4 apples and starting over with a smaller number. So for the size of A, you're really just, so if it helps you, if you prefer this, guys, you can just think about these conditions as being soft inequalities. Sometimes people prefer this, and I don't mind it at all. Strictly greater than a certain number just means greater than or equal to the next number. So I just have to take 4 stars out of the whole problem here, right? So instead of 19, choose 3 for the size of A, I'm gonna lose 4 of those stars and be down to 15, choose 3, right? By the way, I'm gonna keep the 3 on the bottom always. I will always have 3 bars, right? It's just we're reducing the number of stars. If you give the first child 4 of the stuffed animals before you even really have to make any choices, then you're only really thinking about distributing 12 other stuffed animals with the 3 bars to go with it. That's 12 plus 3, 15 stars and bars, and I just choose my 3 bars. Make sense? Okay, the next one, the size of B, that's the same thing, except instead of subtracting 4, I have to subtract 5, which just cuts this down to 14 choose. So you're gonna see how fast this goes once you get the hang of it. It's actually very fast. All right, the next one is 13 choose 3, and the next one is 12 choose 3. Because you're just taking 1 more star out in each case as you go along. Okay, so far so good. Now I have to subtract the 2A intersections. And for the 2A intersections, there will be 6 of these terms. If I look at the intersection of A and B, now I'm taking out actually a total of 9 stars. So, right, so the 16 stuffed animals gets reduced to 7. 7 plus 3 bars gives me 10 stars and bars, and I'm choosing 3 of those. Okay. Agreed? And then what about with A and C? Well, now the number of stars just went up by 1 again that you have to distribute ahead of time. So if you've already passed out 10 stuffed animals, then you only have 6 left, plus the 3 bars, that's just 9. Choose 3. And then if I do A and D, we're gonna subtract 11. You're basically just subtracting these numbers from the 19, right? So 19, you subtract 11, you get 8, so 8 choose 3. Okay, and then we have to come back up here, so that was A intersected with D, but then we have to intersect B with C. That's also 11, so I get another factor of 8 choose 3. And then B intersected with D has 12 stars. If I take those out, I'm down to 7 choose 3. And then C intersect D gives me 13 stars that I have to remove. That leaves me only 3 stars, 3 bars, which is 6 choose 3. Yeah, question?
Go over why there's 2 8s there, like.
Because 4 plus 7, which is the A intersect D term, is the same as 5 plus 6.
Okay.
So the number of stars you're removing just happens to duplicate on that one term. Yeah, good point. Everybody else okay so far? Yes? Kevin? Yep, good, okay, great. Now let's start adding. I have 3-way intersections to take care of. So for A, B, and C, I already have to remove 15 stars. I only have 1 star left. Together with 3 bars, that's just 4 choose 3. Right. And then A intersect B intersect D, that would be 4 + 5 + 7. So you're giving this kid 4 animals, this kid 5 animals, this kid 7 animals, you don't have anything left to give out. There's really only one way to do it, and that could be reflected as 3 choose 3. A intersect C intersect D, now you're running into the impossible. You cannot give 4 animals to A, 4 animals to the first child, 6 to the third child, and 7 to the fourth child. You don't have that many animals to play with, so this becomes 0. And then obviously, actually, all of the rest of the terms are going to be even more stars involved, and so it won't work for any of those other scenarios. So the rest of the terms are all 0. That would be the final answer. Whatever this comes out to, well, I'm sorry, this isn't the final answer. These are the violations, right? So your final answer will be 19 choose 3 minus all of this. Okay, so the final answer by subtraction, really. Final answer is 19 choose 3 minus all of the stuff we just wrote down. I'm just gonna draw an arrow with a little ditto symbol, if that's okay. Save us all a little bit of writing. Okay, and I'm sorry, I did not actually work out what that number is. But it should be greater than 0, which is better than I can say for the first question I had up there. Okay, excellent. Actually, if you had 25 here, 25 animals, then that would mean you'd have more stars. So, you'd have bigger top values in all of these. And so you actually wouldn't get the zeros showing up here because your violations actually make more sense now. If you had 25 animals, well, yeah, you could give 5, 6, and 7 of them to the second, third, and fourth child. So you would actually get a bunch of terms that all made sense. You wouldn't have any zeros showing up here. But what you would know is that if you actually subtracted and did the alternating pluses and minuses, that it would have to add up to 0. Just by common sense, it would have to add up to 0. You do not have a way of giving 25 animals out, given that so many of these kids have a maximum requirement. Make a little bit of sense? Okay, kind of cool. I like that. Let's do the proof of this inclusion-exclusion principle, and that will at least allow us to believe what we're doing. I always get nervous when people start using their results before they've proven them, is what I've just been doing. But let's give a proof. I think this is kind of a nice proof. It's actually not that long. So I'm going to prove this formula, this long, messy formula here for the inclusion-exclusion. Basically, what I'm going to do is try to convince you that every single X that belongs to this union, it gets counted a net total of 1 time by the right-hand side. It might get counted positively several times and negatively several times, but the net total on the right-hand side should come out to +1. And if we can say that about every single element that's in the union, then it feels pretty solid that we've done an accurate count of the size of this union. So that's exactly the way that this proof is going to work. Let's actually write that down. So the proof of the inclusion-exclusion principle, I'll just abbreviate it as IE principle for now. Okay, this is a proof that I definitely think you guys will want to know. So we must show, I'm just going to kind of outline what I just was explaining a moment ago. We must show that every X that belongs to the union of A1, A2, and so on, ... union to AM, gets counted. It gets counted a net total of 1 time by the right-hand side, which I might, as we've done before, just abbreviate RHS as we go forward here. Okay? just without loss of generality, if I write WLOG, does everybody know what that means? You've seen that? Has any other professor ever used it? Without loss of generality. Okay, great. Let's just assume that X, so I'm going to assume that the X that we are looking at that's in our union, since it's in the union, it has to be in at least one of the sets. Let's assume that X is, that X belongs to A1 and A2 and so on up to, let's say, a K. All right, but doesn't belong to AK plus 1, AK plus 2, and on and on and on, dot, 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 up to AM. So just without loss of generality, let's say that this X lives in the first K of the sets, but doesn't live in any of the other sets that are coming later on. Does that seem reasonable? This would be where K, I guess I should explain, this would be where K, obviously, K is at least 1. Let's just say it this way. So 1 is less than or equal to K is less than or equal to M. So the K has to be somewhere in that range. Okay, so I said that I would like to argue that X gets counted a net total of 1 time by the right-hand side. I would like to figure out how many times it's counted here, and then how many times it's counted here, and then how many times it is counted here, and so on. I'm going to do this one term at a time, one summation at a time. So like, for example, how many times does X get counted when I'm adding up the sizes of the singletons? And how much contribution does it make? It gets counted in A1, gets counted in A2, it gets counted in A3. The first K of the sets, right? So K times. Right, exactly. So that's the first observation, is that note that X contributes K times in the summation I going from 1 to M of the size of, I'm sorry, yeah, let's just say I going from 1 to and M of the size of AI. Okay, so far that's K contributions and they're all positive. All of those are positive. Okay. Now, the next thing is how many times, so similarly, go down to another line here. Similarly, X contributes, I'm going to leave a space there to fill this in a second. I'd like to think about how many times it contributes to the summations of the two-way intersections. I'm going to just write it as a summation of the size of AI intersect AJ. So how many of these terms here does X belong to? This is the question. Sergio, you want to give it a shot?
K choose 2.
K choose 2 is right. K choose 2. How is that? Well, I'm basically saying I want to intersect 2 of my sets and X better be in both of them. Well, how many ways could that happen? Well, X lives in these sets, right? So how many ways can I choose 2 of these sets that X belongs to both of and therefore belongs to their intersection? The answer is you've got K sets and you're going to choose 2 of them. You don't care what order they're in, but you want to know how many there are. There's K choose 2. So right here in the notes, guys, we're going to add K choose 2. Now, this, of course, ultimately is going to come with a minus. We are subtracting the two-way intersection terms. Okay, right. So let's write down maybe one more line of this, and then I think you're going to have the idea. Suppose that we go to the three-way intersections, right? How much do you expect X to contribute, or how many terms of that summation that involves the three-way intersections do you imagine that the X contributes to? K choose 3, exactly. It's just K choose 3. So X contributes K choose 3 times in my summations, and I'm being a little loose with my summation notations here, but that's should be understood from the way that the theorem was stated. So the summations of all the AI intersect AJ, intersect AKs, these are gonna be back with pluses again, and there's K, choose 3 of those. And this just keeps on going, right? You know, eventually you'll get to terms near the end of the summation where the answer becomes 0. Because if X doesn't belong to all of the sets, then it contributes nothing, for example, to this last term. So at some point, once we've got more than, I mean, I guess what's the last one that we would have? The last time that this is gonna actually be a meaningful contribution is gonna be when we have K choose
Then minus one.
K choose K, right? As this bottom number gets larger and larger, as soon as it gets bigger than the number on top, you're down to 0, right? So the last one is, maybe can I add one more line? I'm just gonna do it up here though. If that's okay. So lastly, X contributes K, choose K, which is only 1, time in the summation involving, well, actually, I don't even need it to be a summation because it's not even a summation. There's only one term that it contributes to all of, and that would just simply be A1 intersected A2 intersected up to AK. That would be it. Any other intersection involving K of the sets, X is not part of. Go ahead, Jose.
On the third one, should that be a different index to K?
I wondered if anybody was gonna pick on me for this. This K right here has nothing to do with the K that I've used in my proof here. It's just an index of my summation. So you're absolutely right that, you know, by the time I've taught this class another 4 or 5 times, I'll probably remember that I shouldn't use the same K here that I'm using here. But I think you guys can understand. This is just literally an index. Good point. That somebody's paying attention back there. This is either with a plus or with a minus, and we can kind of tell, it just depends on whether K is even or odd. All right, so what it would be is actually -1 to the K plus 1, I believe. So it's, if we're putting our little in parentheses thing here, and then times K, choose K. So I think I have that right. Okay, so let's just add all of that up. Let's see what the net total is. The net total is supposed to be 1. But let's see what it actually seems to be according to our little calculations here. Let's just see what it comes actually out to be. So thus, the net total number of contributions for X is, well, let's see, it was K, but then we had to take away K choose 2. And then we had to add back in K choose 3. And then we had to subtract the next one, and it goes ... The last one is a -1 to the K plus 1 times K choose K. It'd be something like that. And by some miracle, is that possibly going to be equal to 1? What is this? Well, it's not going to be by a miracle. It's going to be equal to 1 by something we all know and love very well, which is the binomial theorem that we just did in the last chapter. Let me show you how that works so we can apply the binomial theorem . Yeah, this is the magic of it. It's the binomial theorem, which is kind of surprising. Maybe you don't think that this is gonna have anything to do with it, remember the binomial theorem is the one x plus y to the n is equal to the summation as I goes from 0 to n. I'm using an I for the index here so that I don't use k again. Out of just trying to avoid that. And it would be n choose I times x to the n minus I times y to the I. And we can apply that theorem with, and here's what I'm going to apply it with. I'm going to apply it with x equal to 1 and y equal to -1. Kind of interesting. So I've got a little colon here because I'm going to keep the calculation going on the next line, but just so you can see it, this is the binomial theorem. We did this the other day. We plugged numbers into our theorem. We don't even need to take an integral or a derivative like we were doing in the group work on Tuesday. Here, we literally just add 1 and -1. We get 0, obviously on the left side. And then on the right side, if I put in a 1 for x and a -1 for y, I am going to get a summation here. I going from 0 to n of n choose I times -1 to the I. Okay. And I want you in your head to be, we did use an n for this exponent, but I want you to be thinking of it as playing the role of the k, because ultimately the k is what we have up here. So you'll see that. Let's just write out a couple of these terms. So when I is equal to 0, we have n choose 0. By the way, that's 1. And then when I is 1, we have n choose 1, but it has a -1 on it. And then we're going to have a plus n choose 2 and a minus n choose 3 and so on, dot, dot, dot. And the last term is going to be plus -1 to the n times n choose n. And this is a 1 right here, guys. I'm going to throw everything else to the other side of the equation. So I'm just going to rewrite it now for you. In other words, if I move everything else to the other side, I'll have n choose 1 minus n choose 2 plus n choose 3 and minus and dot, 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 alternating like so. So the signs are all flipping. So the last one will become -1 to the n plus 1. All of that goes to the left side and leaves me with just equals 1 on the right side. You with me? And do you see that if I just change the n to a k, I literally get the thing that I was claiming right here. I was claiming that if I take k minus k choose 2, add k choose 3, subtract k choose 4, alternating all the way to the end, that it does equal 1. And now I'm seeing that that really is true. That really is true. It's just, I should have just used a k for this exponent, but I wanted to use the binomial theorem the way we stated it. So just replacing, so I'll just say replace n with k to finish our claim. Our claim, maybe I'll call the claim star. I can just put a little star here. That helps you identify the things in the notes that we're proving. Question?
Explain why you changed the index to n plus 1 in the last one.
Because I'm actually moving all of this stuff to the other side of the equal sign. So I'm leaving this 1 right here, but this subtracted term now becomes an added term. This added term becomes subtracted. The signs have actually changed on all of the terms. Yeah, that's how it works. Does everybody follow this? Kyle?
So you can just put a negative sign in front of the -1 to the n power. You have to move it over by 1 just in case it's.
Well, if I wanted to, I could leave all of this stuff here and I could just take this 1 and move it to the other side of the equation. Then I would have -1 equals sort of all of these binomial coefficients with opposite signs to what we actually wanted. So I was just trying to make, because this is really K-choose, one right here, right? I was just trying to make this part that I circled exactly like the form of this left side. And so that did require me to do a sign change on every single one of those terms. It's just the algebra.
I think
Yeah,
he's just saying on that last one, instead of changing the power, you could just put a minus.
I could put negative of -1 to the
Yeah.
end. That's also, if that's what you meant, yeah, I could easily do that too. Yeah, no worries. So this is just one more power of -1 that comes from the n powers with another minus sign there. Yeah, totally good. Yeah, thank you. That's a good point. Oh, you guys were asking the same question?
Earlier today.
Yeah.
Oh, earlier today. Okay. Okay, yeah, no, well, here it comes. Right on cue. Anybody else have any quibbles with anything up here on this crew? So I think that does it. I think that does it. Everything in the union of the M sets gets counted exactly one time if we take this alternating series of summations. Okay, fantastic. I am good with that. Yeah, I think the next thing we're gonna cover is that a hint?
Yeah, just one question.
Please.
Just get it like commentary. So the letting x equals 1 gives you the y term by itself. And then the -1 is the alternating part.
Yeah, the choosing a negative value to plug into your binomial theorem is a good idea when you're trying to work with an identity that has alternating terms. So if you are trying to prove something, I'm sure there's something in the homework on this also, where you have terms that are going plus to minus, you wanna think about the binomial theorem potentially with the use of a negative value being plugged in, at least for one of the unknowns. Yeah, that's
So it doesn't have to be the y.
no, it wouldn't have to. The only reason I chose the y instead of the x is I didn't want to have -1 raised to the n minus I. I just wanted the -1 to the I, just to make it cleaner. But it's totally, it's just, it's a minor point. Doesn't have to be that way. Yeah. Okay, great comments, guys. Really appreciate all the dialogue and the questions. And of course, there's generally many ways to look at some of these things. So I appreciate the different perspectives. Okay, so we've got this thing proved now, so now we can use it. We can use it as much as we want. Maybe on Tuesday next week, well, what we're gonna do next week, I think I'm gonna pause so I can help you with the homework now, but what we're gonna do next week is we're gonna talk about derangements and forbidden position problems. So these are really fun problems about permuting objects with lots of constraints. So if you have, if everybody in this room is wearing a hat and we all go to a party and we check the hats, the question would be, what's the probability that if the hats get randomly passed back, that nobody has their correct hat anymore? And that can be explained using the inclusion-exclusion principle. That's the famous hat check problem. I'll tease you with that to come back next week, because I think you're gonna wanna see that. But I think what I'd like to do now is help out with a couple of the homework problems. I know at least one that was being asked of me earlier when I could barely think. Now that things have calmed down, I think I can probably be a little more helpful. So this is the homework. Again, if you came in late, the homework is not due tonight. I'm gonna give you until tomorrow night to finish it, and I'm gonna have office hours tomorrow as well. Let's look at chapter 5. This is where all these problems are mostly coming from. This is where most of the problems are coming from. And I wanna look at number 12. I think that's one that people would like to see. And again, if you've already turned in the homework, you can always unturn it in and resubmit a new version. Number 12 from tomorrow's homework.
Did you get to number 12?
So everybody's gonna follow my notes, right? And then if I choose to grade this one, it's gonna be super easy, I hope. And of course, if I take off points, that'd be really embarrassing for me. This is probably what I wrote down. So hopefully I do it right. So this is saying for a positive integer n, let's prove that the summation k going from 0 to n of -1 to the k times n choose k squared, that is equal to, and there's two possibilities depending on whether n is even or odd. So it's gonna equal 0 if n is odd. And it's going to equal -1 to the m times 2m choose m if n is even. And of course, if n is even, it's going to be written as 2 times m. That makes it into an even number. And so this is actually two problems because you have to prove the odd case and then you have to prove the even case. And there's a hint. And the first thing that I think is confusing already is they make it sound like the hint is only for the second case, but it really is helpful for both cases. So for the solution here, they give you a little hint. And what the hint is, I'll just write the hint here. The hint is simply that if you take the quantity 1 minus x squared and raise it to the nth power, that because you can factor the 1 minus x squared as 1 plus x and times 1 minus x, you can break this up as a product of two terms. So we are going to use this hint to help us out here. So let's prove the odd case right now. So let's assume, is that okay? Or does anybody want to, or maybe somebody's already done this, wants to suggest an idea, but I'm kind of just, I get excited and then I just kind of go into it. So, but if you don't want me to do that, I'll put on the brakes a little bit.
I was able to work out that one of the sides is you just it's basically Pascal's, it's rows on Pascal's triangle, and if you sum alternatively each odd row, then things cancel out and you get the 0. Sorry, the even ones they cancel out and you get the 0, and if it's
Okay.
the odd ones, then it's just the value that's in the middle.
I see. Okay.
Yeah.
Yeah, let me write down some stuff here and see if it lines up with what you're saying here.
Okay.
I'm gonna do this in two cases, so I'm gonna just start with, let's assume that n is odd. So this is the first case, and what I would like to do is, I would like to look at the coefficient of x to the n on both sides of the equal sign. You would agree they'd have to be the same, because this thing is equal to this thing. So whatever the coefficient of x to the n is on the left has to be the same as the coefficient of x to the n on the right. So consider the coefficient of x to the n. Now on the left-hand side, this coefficient is, can somebody tell me what is the coefficient of x to the n? If I was to multiply this out, imagine foiling it out, 1 minus x squared times 1 minus x squared times 1 minus x squared. You just multiply all of that out. Just think about what kind of terms you'd be getting. N is odd. What would be the coefficient in front of, say, x to the 7th or x to the 9th? If you foiled out 1 minus x squared times 1 minus x squared times 1 minus x squared, if you just expanded that all the way out, what would be the coefficient of x to the 5th or x cubed or
0.
0, right? Exactly, because how do you find the terms of this expansion? You go through and you pick something from each factor, right? You either pick this one or you pick this one or whatever, but you're always picking the x's 2 at a time whenever you are picking the term that has x in it. So on the left-hand side, you don't have any odd powers of x. That's really all I'm saying. You could show this to a pre-calculus student and give them n equals any odd number you want, n equals 3 or something, and just FOIL that out. You'll see that there's no odd powers of x. So this coefficient has to be 0 on the left-hand side. There are no x to the odd powers. You with me?
Mhm.
Okay, now let's think about what the coefficient of x to the n would be if I view it from the perspective of the right-hand side. Now that's the harder part of this analysis, because you've got some 1 plus x's and you've got some 1 minus x's. So you've got, 1 plus x times 1 minus x times 1 plus x times 1 minus x and so on like that. You're going to pick, you've got 2n factors total here. And as you're kind of making a term out of the expansion of those 2n factors, you're gonna grab either the 1 or the x here, and either the 1 or the x here, and either the 1 or the x here, as you make a term. But by the time you've gone through all 2n factors, you were supposed to have picked the x n times. Because if you're making terms that have x to the n as their expression, then you've got to pick that x n times. In other words, half of the times. Half of the times you're going to pick the 1, half the times you're going to pick the x. But you could pick the x k times from this guy and n minus k times from this guy, right? You see, you've got n of these, you got n of these. So you can pick the x, say k times here, and then n minus k times here, whatever k is. Could be 3 times here and n minus 3 times here, for example. But that k could vary. The k could be 0. Maybe you don't pick any of these x's and you pick them all from over here. Or k could be 1. You pick one of the x's from these n factors here, and then n minus 1 of them from here. The point is you're picking some of these x's and some of these x's, right? And when you pick these x's, those have coefficients of 1. These x's have coefficients of -1, right? So on the left-hand side, or so on the right-hand side, this coefficient is, well, first of all, it is a summation over some k value that I keep talking about. I'm going to write it as k. K could be anything from 0 to n. In your mind, what I want you to be thinking about is k is sort of breaking down how many of the x's are coming from the first factor versus the second factor of these two pieces. Okay, it's kind of the idea behind it. So actually, I'm going to think of it as I picked this x here, n minus k times, out of a total of n places where I could have picked it from. So how many ways are there to do that? So I'm just looking at the first factor. I've got n factors of 1 plus x sitting down side by side, and I want to pick the x n minus k times. Pick is just another word for choose. I would like to choose out of these n factors. I would like to choose n minus k of them to pick the x, right? So I'm going to do that. I'm going to take those n factors and I'm going to choose the x n minus k times. I also, with the second, I have the same task over here with the 1 minus x to the n. I have to pick the x k times. I choose it or pick it from the n terms that I have. That would be n choose k. But every time I pick this x, I'm also grabbing the negative, because this is all kind of put together, right? The negative and the x goes together. So that -1 gets picked up along with those x's that we are seeing there. And of course, n choose n minus k is the same as n choose k. So this just becomes the summation k going from 0 to n of n choose k squared times -1 to the k. And because the left side and the right side have to be equal, right? Because it's the same algebraic identity, then whatever the coefficient was on the left side has to agree with the coefficient on the right side. So let me just, for your benefit, for your looking at this in the future, I'm just going to make a quick note here that k denotes the number of factors of x taken from 1 minus x to the n. So that second part of it, 1 minus x to the n, there are n factors, and I'm going to choose x, k of those times. N choose k is the number of ways of doing that. Okay, Okay, and so since the left-hand side equals the right-hand side, we get our identity, right? The summation k going from 0 to n of -1 to the k times n choose k squared adds up to 0. This is all in the odd case, when n is odd. Okay. While I'm erasing, take a look at that, see if there's anything you think needs a little more clarification. Seems okay? All right, well, the good news about this is that to do the even case, you more or less go at it the same way. So I don't know if this is lining up with what anybody else has been thinking about, but this is basically the way I like to think about this problem. So if we assume instead that n is even, I again want to consider the coefficient of x to the n. And on the left-hand side, the coefficient of x to the n is, okay, so now, let's slow down a moment. Now we will get, if it's an even power of x, we will see those on the left side. It's not going to be 0, right? So the question is, well, obviously the power of x could be as little as x to the 0, or it could be as much as x to the 2n. X to the n is sort of halfway in the middle. And what it means is that I'm taking this expression and I've got to grab either the 1 or the x squared each time, right? And I need to grab this x squared half the time, actually, so that I get, I'm not going to grab it n times, I'm going to grab it basically n over 2 times, which is, in other words, m times. I'm going to grab this x squared m times. And if I multiply x squared by itself m times, I get x to the 2m, which is x to the n. That's what we're looking for. So the question is really just, out of these n terms, I have to choose m of them in which to grab the x squared. And all of the other ones, I'll grab the 1. You with me? How do you make terms out of this thing, guys? You imagine foiling it out. And as you FOIL it out and you start taking products, you're going to either multiply by a 1 or an x squared every single time. To get an x to the n to show up, I have to pick this x squared m of those times out of 2m available factors. Okay, so the answer is, out of those 2m available factors, I have to choose the x squared m of those times, right, which is half of the times. And every time I do that, every time I pick that x squared term, I'm also picking up the negative that came with it. So there would have been a -1 being picked up m of those times, right? Well, and you see immediately that's what you're hoping to say here in this case. Okay, so maybe I should just say, since we choose x squared from m of the 2m factors in 1 minus x squared to the n. Yeah, so that's the idea there. That's looking at it from the perspective of the left side. But the perspective with respect to the right side is actually just the same as before. It's just the same as before. The right-hand side, you're just, what is the coefficient of x to the n on the right-hand side? Nothing in this explanation here was really depending on n being off. For this piece of it, it was really just saying, well, I'm going to grab some of the x's from the 1 plus x factors and the rest of them from the 1 minus x factors. As long as at the end of the day, I've grabbed a total of n things, I'm going to get the coefficient of x to the n. So just as in the odd case, the right-hand side measures the summation k going from 0 to n of -1 to the k times n choose k squared. So that does not need to be re-explained. That part is literally the same as the odd case. Does that make a little bit of sense? This one probably, take your pictures, take your notes, whatever. I would come back to it and just convince yourself one more time of this, like 5 hours from now or something. Make sure it still seems reasonable to you. It does take a little bit of thought. It also took me longer to explain it than I had wanted to. Can anybody tell me, were there any other problems from the homework that you wished that I had gone over right now?
The second part.
I know, that would have been what I would have picked, if I had wanted to, if I had had a few more minutes. Were there any others that were particularly annoying?
The first problem from chapter.
Oh, from chapter 2?
uh,
Oh, number 48, okay.
That one was, I don't know what to do.
How would it be if I kind of like my YouTube channel. I haven't done something lately. If I just went into a room this evening and just made a video of these two problems and then just kind of set it out overnight sometime,
Yeah.
would anybody watch it? Okay, good. Okay, I'll do that. That'll save you a little bit of headache. If there's any others besides those, I do have those extra office hours tomorrow. If you can't make my office hours, you can also shoot me an email. Just say, hey, Dr. Annan, I'm stuck on number 15 or whatever problem it is, and I'll try to talk with you over the email about it. All right, guys, thanks so much for a great week. I really enjoyed this stuff this week. I hope that you did too.